Okay, let's open a really fascinating time capsule today. We're looking at Pierre Curie's 1905 Nobel Lecture. This was, what, just a few years after radioactivity was even discovered.
Barely. It was incredibly early days.
Right. So our mission here is to unpack what Curie shared right then, those immediate kind of earth-shattering insights about radium and what it meant for science.
Well, it all kicked off with a real puzzle. You had Henri Becquerel finding uranium emitted these faint, steady rays.
Okay.
But then Marie Curie starts analyzing minerals, right, like pitchblende.
Hmm.
And she finds they're way, way more radioactive than they should be, just based on the uranium or thorium inside.
So more activity than the known radioactive elements could account for.
Exactly, which strongly suggested there had to be something else in there, something unknown.
And that led them to polonium and radium.
Precisely. Polonium, chemically similar to bismuth, and then radium, which was near barium, but wow, its activity was just staggering.
How staggering are we talking?
About 2 million times more active than uranium. 2 million.
That's hard to even picture. I mean, where was all that energy coming from? It defied physics back then, didn't it?
Completely. And the amazing thing was, this wasn't just a theory. You could actually measure the heat. Pierre Curie and Laborde, they confirmed it. 1 gram of radium constantly gives off heat.
Constantly. Like a little furnace.
Yeah, about 100 calories per hour per gram. And it just keeps going. Over time, that adds up to a, well, considerable amount of energy.
And this energy wasn't just heat, right? It was radiation. They started figuring out there were different kinds.
Physicists like Rutherford, Villard, others, they used magnetic fields and found 3 distinct types of rays.
Okay, what were they?
So first you had alpha rays. These were positively charged, relatively heavy particles, a bit like Goldstein's canal rays, if you know those.
Got it. Positively charged, heavy. What else?
Then beta rays. These shot off in the opposite direction in a magnetic field, so negatively charged. They were basically high-speed electrons, tiny things, like 2,000 times smaller than a hydrogen atom.
Electrons, okay.
Yeah.
And the third type?
Gamma rays. These weren't deflected by magnets at all. Very penetrating. Similar, they thought, to Roentgen's excerpts.
Alpha, beta, gamma.
Oh.
Okay. So this relentless energy, these rays,
Yeah.
it posed a massive question for chemistry, right? For the very idea of the atom.
Huge. The atom was supposed to be, indestructible, unchanging, for 2,000 years. So where did this radium energy come from? There were basically 2 initial ideas.
What were they?
Well, one was sort of conservative.
Hmm?
Maybe these radioactive substances were somehow capturing energy from outside themselves, from some unknown cosmic source, perhaps.
Okay, borrowing energy. What was the other idea?
The other more radical idea, and the one that turned out to be much more fruitful, was that the energy came from within the radium atom itself.
From inside the atom.
Yes, which implies, well, it implies the atom isn't stable, it must be changing, evolving somehow, transforming very slowly over time.
Changing. So the atom itself is the source.
Exactly. And this is where Rutherford and Soddy came in. They developed this theory of continuous and irreversible disaggregation of the atoms.
Disaggregation? Like falling apart.
Pretty much. The atom's very existence, its stability, was suddenly at stake, as Curie put it. This wasn't just a minor change. It was a full-blown theory of the transmutation of elements.
Transmutation, like alchemy.
Yeah.
Turning one element into another.
In a way, yes. A scientifically rigorous version of it. Suddenly, things made sense. Like, why does polonium just seem to fade away? Its activity drops by half every 140 days.
Because it's transforming into something else.
Precisely. And why does radium constantly produce helium gas? Because helium is one of the products of its decay, its transformation. We now know alpha particles are helium nuclei.
Wow. And does this connect to geology at all?
Absolutely. When they looked at minerals, they consistently found a fixed ratio between the amount of uranium and the amount of radium.
Implying
Radium is constantly being produced by the decay of uranium. It fits the transmutation picture and hints at these processes happening over immense geological timescales.
Okay, so it revolutionized chemistry. What about physics? You mentioned those beta rays, the electrons.
Ah, yes. Studying those extremely fast beta rays led to another bombshell. They confirmed a theory by J.J. Thomson and Heaviside
Which was?
that an object's mass isn't constant. It actually increases the faster it moves.
Mass increases with velocity. That sounds very non-Newtonian.
Exactly. It was a fundamental challenge to classical mechanics. It suggested that maybe the particle's entire mass was electromagnetic in origin. That mass itself was a form of energy, a huge step towards Einstein's immensity, though that was still just around the corner.
Incredible. But there were more immediate practical consequences too, weren't there? Biological effects.
Oh, definitely. They quickly realized these rays had potent biological effects. They started using them cautiously to treat diseases, lupus, even some cancers. Radium therapy.
But they also knew it was dangerous.
Very much so. Pierre Curie himself described it starkly. He mentioned if you just carried a small tube of radium salt in your pocket for a few hours,
How would it happen?
you wouldn't feel a thing at first. But about 15 days later, a red mark would appear on your skin, turning into a sore that was really persistent and difficult to heal.
15 days later. That's quite insidious. Shows how little they understood the long-term risks initially.
Right. And that potential for harm, alongside the immense power, led Curie to end his lecture with a really profound, almost moral question.
Which was?
He asked, essentially, could this knowledge, this power of radium, be dangerous in the wrong hands, in criminal hands? And more broadly, does humanity actually benefit from uncovering nature's secrets like this? Or is some knowledge too harmful?
A heavy question. Did he offer an answer?
He did. He brought up Alfred Nobel, whose invention of dynamite was both a tool for progress and a weapon of war. Curie expressed his own belief, his faith, that ultimately humanity would find ways to derive more good than harm from these new discoveries.
A hopeful note, then.
Hopeful, yes. But the underlying point he left listeners with was just how fundamentally things had changed. The idea that matter itself isn't fixed, but is constantly evolving, irreversibly. That's the truly staggering takeaway from that moment in time.